Okay, hello everyone, my name is Jasmine Good and I'm a geology major at Phoenix College. Over the summer I had the opportunity of participating in a research experience program with ASU, a part of the CBBG, which is the Center for Biomediated Bio-Inspired Geotechnics. Basically, their goal is to combine engineering, biology, and geology and apply it to our everyday lives. I had the project of investigation into the geology of Ottawa sand samples for enzyme induced carbonate precipitation. Enzyme induced carbonate precipitation is they take the enzyme of a jack bean and they take sand and they put it in the enzyme and they create sandstone. So here's the sand and the sandstone. And my focus, like the importance of the EICP treatment is like you think of like going to the beach. If you want to build a house on the beach, there's going to be sand there, right? Well, a lot of times in California when it rains, the sand gets overly saturated and like they'll have an earthquake like the ones that just happened recently, and it'll be something called liquefaction where the sand is not stable enough to hold the property that's on it and it sinks. So what the aim of EICP is to do is that they want to solidify the sand to make a solid foundation so when the rain comes it won't have that liquefaction quicksand effect. And I studied the specific sand that they were using for the EICP treatment because they tested 3 different Ottawa sand samples. And Ottawa sand is, it's basically sand from Ottawa, Illinois. And they grind it mechanically. It's quartz stone, like this one. And they grind it with a metal grinder mechanically to produce the sand. And they use that to test the EICP treatment. And they bought 3 different sand batches from the same company, and they all ended up looking different. This is the oldest one they had, the old sand sample, and then the intermediate sand and the new sand. And you can see like they don't look that much alike. The old sand is just plain beige, and then the intermediate sand has like black speckles in it, and the newer sand has black speckles and has some orange in it too. And when they did the test on these sand samples, normally what they do to test their durability and strength is to compress them. And so they did the compression test on these 3 different samples and found that they had significantly different results. The old sand was the strongest of the 3 and the new sand was the weakest. And so they said, well, why are they so different and they're from the same manufacturer? They're supposed to be the same sand. And they said, could it be the fact that they look so different? So I decided to do some research into that. And we used an AFM, which is an atomic force microscope. So you think of a regular like school microscope, you can see like bacteria in it and the tiny little life cells. Well, think of this microscope, it looks at it on an atomic level. You could see the surface of those bacteria. So we were spending our time looking at the surface of the sand grain, saying, okay, well maybe the way they were grinding it, it was different, and so the surface wasn't sticking as well. And maybe whatever these black grains were, that they were having a different like adhesion to the EICP treatment than the beige sands, the quartz sands. And this is a picture of one of the black grains, and you see it has like this smooth kind of plain surface and this bumpy surface and this interface right here. And that was typical of a lot of the black sands. They had like that weird irregular pattern. With the quartz sands, it was just more like you think of smooth, bumpy hills. But we looked at like the surface roughness of them to see like how well they were going to adhere. When you think of scoring clay, it's better to score it because it'll stick together better than just not scoring it. So we were thinking that that was the reason why it wasn't sticking well, but the roughness of the sands didn't seem to have an effect at all on the sand samples. And so then I looked deeper and I said, well, what is the sand made of? And I know they're making EICP treatment, which is, it produces limestone, which is like these rocks right here. These are limestone, and so it's a natural cement that's sticking the sands and everything together. And I was like, is that maybe, are they using like a different method, or like how is it affecting it? And that didn't seem to be affecting any of the sand properties of it sticking together. And I went to the quartz next. I was like, well, maybe they're using different quartz. Quartz has different varieties. You have like the amethyst, which is purple quartz, and then you have your pink rose quartz, and then you have smoky quartz that has like a little black color to it. So I said, is that maybe affecting it in its properties? And that didn't seem to have any effect on the element itself. But one key thing that they found while they were doing analysis on the sand was that it had iron oxide in it. And iron oxide is like rust. You think of Sedona rock, and this is a rock from Sedona, and you see how it's red, so you think, you can kind of tell like the orange and the kind of blackish red rocks in here, that may have something to do, that's probably a case for something going on in the sand. But another form of iron oxide is magnetite, and magnetite is iron 2,3 oxide. That's the chemical name for it, whereas rust is iron 2 oxide. And the magnetite, what's so special about it, this is a stone form of magnetite, is that it is a strong magnetic material, and it will either attract or repel magnetic forces. And so what just happened to be the problem here is that we were able to discover that, okay, magnetite is a common sand particle that's found in a lot of sand samples, and this is iron oxide can match up with the magnetite, and that magnetite has a magnetic force called ferromagnetic, where it attracts or it repels. It attracts or it will be attracted by a magnet. And the limestone, it was diamagnetic, which means that any kind of magnetic force, like the ferromagnetic force that it encountered, it was going to move away from it. So that's what was happening with these sands. The newer sand had much more of the magnetite in it than the older sand, so it was moving away from, the limestone was moving away from these black grains, so it wasn't sticking together as well. And that's why the compression test failed. So to conclude, all of the sands were the same. The black grains that we found in the intermediate and new sand samples were magnetite, and the topography, the surface roughness that I mentioned, it was jagged, and the quartz sand was smooth, but didn't have much of a difference between the adhesion of the EICP, and the forces between the limestone and the magnetite were repelling against each other. All of my sources were, I found the USGS, U.S. Geological Survey, the School of Oxford University, the Department of Engineering faculty at the University of Indonesia, the School of Chemical Engineering in Busan, Korea, and the Department of Sweden for Anthropology and Geography. Any questions, comments, feedback?
Yeah, what is the basic process? I'm not familiar with. How do they take it from sand to make it to like a sandstone? What do they do? Do they put any chemicals in it, or what do they do?
So natural sandstone is formed over like a process of compression. Like you think of being squeezed between like two weights, and the sand is naturally pressed together, and limestone will come in and cement it. So they try to emulate that process by taking this enzyme from this plant, the jack bean, and they submerge the sand into the enzyme, and it produces that limestone, and that's how they get the samples
in the beginning, you mentioned about in California and houses not being able to stand on the sand there.
Mm-hmm.
I'm just curious as to why they picked Ottawa, Illinois, as opposed to sand in California.
It was due to convenience for the testing, because depending on which beach you go to in California, the sand samples will be very different, and then each time you go, like, the sand samples will be different. So they just wanted to give like a lab like emulation of it to test the sand samples, so they could see if the treatment itself actually worked, and then be able to take it out into different places, because even the sand in California is going to be totally different from the sand in Florida. So they're just kind of doing a lab process of it. Yeah. Anything else?
Was there any studies on it that looked at how much pressure that the actual stones can take, as opposed to something like cement or something?
Okay, so with the EICP treatment, we actually, another study that a group did was on using it for cement too. And comparatively, there's plain cement to the EICP sand. They are about the same. I think the highest, I want to say it was 13 tons. It was a big amount of weight that these little columns of sand that they would test could take. So it was relatively the same as cement. They just want to use more of a more environmentally friendly kind of process than actually making like the cement.
And do you know how it compares in cost, cement, to this process?
Okay, so the cement would be, I couldn't give exact numbers, but the EICP enzyme is from like a jack bean, which is like, you think of pinto beans, and it's relatively easy to like buy. And so the treatment itself can just be sprayed on the sand in California, and the cement, building like the cements and everything, it would cost like considerably more to just constantly treat like all of the grounds with cement, and plus that would mess up the ecosystem for like the crabs and the oysters and clams that are in there. Yeah, this wouldn't harm the animals or any of the biosphere there at all. That's it. Thank you.